Okay, we're going to continue on lecturing chapter 2. Seems like a good one. Why not? All right, last time we talked like about chemistry type things, right? So we were talking about really electrons and sort of moving away from Bohr's model of the atom there. Again, that more sort of planetary model where we have our electrons again moving around in these orbits. Um, as we talked about, works really well for hydrogen, but when you get more than sort of one electron sort of involved, it doesn't really hold up. So we sort of moved away from Bohr's model of the atom to this more quantum mechanical model of the atom, where we talked about things like particles and waves that both share very similar type function. Particles have wave-like function and waves have particle-like function. And the idea of a particle like an electron is at any given point in time, really traveling randomly sort of about the nucleus in an atom in that empty space. And that was the Heisenberg uncertainty principle, which basically again said that the more you know about how it's traveling, the less you know about its actual position. And we move away from orbits to this idea of, with Schrodinger and his equations, what are referred to as orbitals. And these, again, are these more sort of probability sort of maps of a high probability or say low probability of finding an electron in a particular location within the atom. Again, we don't really know how it got there, how it's traveling. The best we could do is just say, there's a pretty good probability that we would find perhaps an electron in a particular location. We know that because the nucleus is positively charged, electrons are negatively charged. We should have a pretty good high probability near the nucleus. And then obviously, as we fan out from the nucleus, our probability should get a little bit lower and lower. Not to say we couldn't find an electron out there, but there's less of a probability than, say, falling an electron closer to that nucleus. So we move to orbitals where the maximum number of electrons that any orbital could hold, again, is 2 electrons. And there are s orbitals, p orbitals, d orbitals, and f orbitals. And we basically talked also about sort of the idea, which is really these sort of mathematical explanations of why we have certain orbitals on certain energy levels and how many orbitals we have and stuff like that. And that was the idea of quantum numbers, I think, where we sort of left off there. And quantum numbers, there are 4 different types of quantum numbers. There's n, which basically go from 1 to 7, and that's, for all intents and purposes, the principal quantum number. Kind of tells you the energy level for the most part, what energy level you're on. N equals 1 is the ground state, or the lowest energy state that there is, and anything sort of above that is considered sort of a higher energy level or an excited energy level. There's also L, which is the angular quantum number, and that could have values of 0 to n minus 1. And for the most part, it sort of tells you the shape of the orbitals. It really tells you the type, for the most part, of orbitals. So remember, for example, if we get an L value of 0, that's pretty much your s orbital. We have an L value of 1, that's like your p orbital, and so forth. Kind of keep counting. And we have m sub L, which basically runs from minus L to 0 to positive L. I guess it's right, to positive L there. And for the most part, it really does sort of give you your orientation in 3-dimensional space, but it also will tell you pretty much the number of orbitals there are in a particular subshell. And we could do an m sub L value for every L value that you have. And again, you could count them, for example, if we did m sub L for 1, an L value of 1, that would be minus 1, 0, and plus 1. And each of these represents a different type of p orbital. That would be our px, our py, and our pz sort of orbital that there are. And then we also have the spin quantum number, which can be plus or minus 1/2. And typically our first electron that goes in will have a positive half a spin. and our second one will have a -1/2 spin when it goes in. So these are the 4 quantum numbers, and really, again, why when we think about something like electron configuration and things of that nature, why we see that on the first energy level, as we went through, I think the only available sort of possible orbital that you could have is a 1s orbital. On the second energy level, there's also s orbitals, but that again is where we start to see the p subshells start to occur. On the third energy level, we also have the s, we also have the p, and that is where we first start to see our d orbitals occur. And I'll go above everything here. Our n equals 4. We have our s, we have our p, we have our d, and I'll go this way, around the room. And that is where we start to see, again, our F's start to appear. So really the quantum numbers are sort of a basis of the orbitals in which we sort of fill electrons as they get put into the atom, and basically where they are sort of on what energy level and where we find them. Any questions on any of that stuff there that we talked about last time? And pass this around, so just autograph next to your name if you could. Okay, so I think just sort of where we left off is we did some of those examples, and we sort of looked at the different orbitals, or S's or P's or D's and our F's. So we're going to kind of put all this together and talk about electron configuration next, and we'll kind of do it here. Now, electron configuration is the order at which electrons basically are filled within an atom, and we usually write electron configuration based on filling order rather than, say, energy. And there is a difference in the energy level of all the orbitals when we have more than one electron. So kind of like what I drew here and what we were looking at, I think, at the end last time, when there's only like kind of one electron, everybody on the same energy level is basically equal in energy. So, you know, everybody on the third energy level is equal to each other, everybody on the fourth energy level is equal to each other, and so forth. When we start to add more than one electron involved, we do get some electron-electron repulsion type of action is happening. And there is really a change in the order at which the orbitals end up. And the major change happens between the s orbitals and the d orbitals. And what ends up happening is the s orbitals actually end up being lower in energy than the d's. So the s orbitals actually get filled first, then the d orbitals, and then it goes backwards. So for example, the first time you come across that is the 4s orbital actually gets the electrons first, then it goes back to the 3d orbitals and then continues on. So there's sort of that s before d is always how it happens when electrons are filled. So there is a order at which electrons go into the atom, and you could recreate it for yourself very easily. You maybe have seen this, and all you really have to remember is on the first energy level, there's s orbitals. On the second energy level, there's p orbitals. On the third energy level, that's where d's start. And on the fourth energy level, that's basically where f's start. And really, if you just remember that sort of order, all you have to do is basically just fill in the numbers underneath, and you'll have the proper electron configuration order. So we're going to try to do this right here. 3s there, 4s, 5s, 6s, 7s, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, and 6d, and 5f. So this is the sort of proper order, and as you can see, within 20 seconds, you can basically recreate the proper order at which electrons get filled. We always start up here, and we basically go through and just kind of zigzag back and forth. And as you can see, we go from 3p to 4s, and then to 3d, and so forth. And again, 5s to our 4d. And you just keep following sort of the order there of the arrows. And again, you always start at the top. Now, knowing this or knowing how to recreate this and knowing what we talked about the other day, that basically the maximum number of electrons that you put in an s orbital is 2. Maximum number of electrons you filled up to p subshell is 6. Maximum number of electrons you filled up to d subshell is 10. And 14 for our f subshell. You pretty much could write any electron configuration that you would need to do by following this order. So we're going to go through electron configuration and write it, and we'll do some examples. And we'll start start with the very first one, which is our friend hydrogen. So if we have hydrogen, and obviously it is neutral, it will have 1 electron. So we are going to start up here. And the first orbital we're going to come across, obviously, is the 1s. So this would be 1s1 would be the electron configuration for our hydrogen. Again, the first number here is the principal quantum number. That is the n number. S is the orbital or subshell that it is in, and that is the number of electrons in it. Now, there's another way that we also can represent electron configuration, and this is what is sometimes referred to as orbital diagram. And orbital diagram is where we use boxes or lines to represent the orbitals. So I'll just use a box here and a 1s, and we use arrows to represent the electrons. So we're going to have 1 electron that goes in the upward direction. And again, the first one does go in that upward direction. First off, any questions on either of those? So tying this into our quantum number discussion here, we can assign the 4 quantum numbers for this electron that we're looking at. So this electron here would have an n value of 1, yes, as is on the first energy level. It should have an L value of 0, right? N minus 1, 1 minus 1 is 0, and 0 represents an s orbital, which is where the electron is hanging out. The m sub L value for this guy would also be 0 in this case. And the spin on this guy would be plus 1/2. So not plus or minus, but actually would be plus 1/2, as that's the first electron in the box there, heading in the upward direction there. Any questions on how to assign those quantum numbers there? All right, so then let's go to number 2 there on the periodic table, which is helium. So helium is number 2 here. Once again, we will start at the top. So starting here, we can, as we can see from our box there, put another electron in there. So this would be 1s2 in this case. So now when we draw our orbital diagram, we have a couple of options maybe as to how we would maybe want to put our second electron in there. We know we have the first one that's going up. There is, I guess, 2 sort of options. We could put the next one up as well, and we could put the next one maybe down. And there is a rule that we follow that was referred to as Paulies exclusion rule. And Paulies exclusion rule basically says that no 2 electrons in the same orbital can have the same 4 quantum numbers. So following Paulies exclusion rule, this is what's going to help us determine sort of which way is the proper way to do this. So before we assign the 4 quantum numbers for our first electron there, And obviously this first electron would hit all four of these quantum numbers. Now, if I also put the second electron in the same way, it would also hit n is equal to 1, L is equal to 0, M sub L would be 0, and M sub S would be plus 1/2. That is the same four quantum numbers as our first electron that's sitting in that orbital. That would be a violation of Paulies exclusion rule, which means we cannot do that. So what we need to do is when we put the second electron in there, it actually needs to be going in the opposite direction, because now if we assign the four quantum numbers for this guy right about here, n is going to equal 1, L will equal 0, M sub L will equal 0, and in this case, the electron is pointing downward, which means M sub S is equal to minus 1/2. So that difference there between the first electron and the second electron means that they do not share the same four quantum numbers, does not violate Paulies exclusion rule. So this is the reasoning that we go with one up, one down. This type of arrangement where we have an electron up and down, opposite spin, this is what is sometimes referred to as the spin being paired. So paired spin is where we have basically our electrons heading in opposite directions in this case. Any questions on that? So always when we put an electron, draw an orbital diagram, first electron goes in upwards, second one should go in the opposite spin location going downwards, pairing off the electrons in that particular orbital. That will allow it not to violate Paulies exclusion rule, and they will have basically they'll have different quantum numbers. They won't share the same four quantum numbers. Any questions on any of that there? So as you can see, you could apply quantum numbers to each specific electron that you put in there, right? So you could really keep track of where everything comes from. So let's continue on then. Let's do number 3 here. And number 3 is lithium. So once again, starting at the top here, we'll go to 1s2. At that point, we are full, which means we then need to zigzag back to our next orbital here, which would be 2s1. So we could count the top numbers there. The 2 and the 1 are the electrons that are in those particular orbitals. And in this particular case, we have how many electrons on the second energy level? We have 1 electron on the second energy level, be that electron, and we have 2 that are on the first energy level in this case. Now, if we were to draw our orbital diagram here, we would have a box for our 1s. We would also have a box for our 2s, and I'm not going to draw it truly based on energy, which means I should really draw the boxes going upwards, but I'm going to run out of room, so I'm just going to draw them next to each other. But obviously the 2s would be higher in energy. If we kind of drew it based on energy, I'm just going to draw it next to each other so I don't run out of too much room. The first electron is going to go in up, second electron is going to go in downward, and the third electron here will go in the upwards direction in this case. So if we wanted to apply our quantum numbers to this electron here, what would the n value be for that electron? It should be 2, yeah. L value could be anywhere from 0 to 1, but in this particular case, which one should it be? It actually should be 1, because actually it should not be 1. We try that again. It actually should be the one next to it there. It actually should be 0 in this case, because our electron is in the s orbital. So our electron's in the s orbital, so it should be that guy. That means that our m sub L value here will be 0, and our m sub S will be plus 1/2 in this case. Any questions on that there? All right, so continuing on, number 4 there is beryllium. So again, starting up here at the top and working our way, we will have 1s2 and 2s2. We now have 2 electrons on the second energy level and 2 on the first energy level. And doing our orbital diagram here. Once again, just kind of draw them side by side, but normally you would perhaps draw them above each other based on energy. First one goes in, second one goes down. First one goes in, second one goes down. All right, so the quantum numbers for the second one that went in there is going to be n is equal to 2. L here will equal 0 as it's still an s orbital, the electron's in. M sub L will equal 0, and our M sub S here will be minus 1/2 as is going in the downward direction there. Any questions on any of those there? All right, let's continue on then to number 5, I think. So number 5 here is boron. And again, we will start with up here and work our way down. As we can see from our previous one, we now will need to work our way to the 2p there at the end. So starting at the top, 1s2, 2s2, 2p1 in this case. And again, our orbital diagram will look something like this. And for the p, I actually will need 3 boxes, right? And that represents my px, py, and pz orbital that's happening. So we will go up, down, and we will put our first electron in the upward box there. Now, when we look at the quantum numbers here for this electron, our n value will equal 2. We can have an L value of 0 and 1, and in this particular case, the L value should be 1 in this case, as that electron is sitting in the p orbital subshell. So L will equal 1. Now, because L equals 1 in this case, M sub L could go from -1 to 0 to +1. And the way this works is pretty much like your boxes. This is going to be -1, 0, and +1 in this case. That means that that electron is actually hanging in the -1, which really represents the px orbital. And the M sub L will be -1, and the M sub S will be +1/2, as it is pointing upwards. Any questions on that? So looking at, we got their carbon next, which is 6. It's going to give us 1s2, 2s2, 2p2 in this case. So we'll have our boxes here. So now in this case, we will go up, we will go down, we'll go up, we'll go down, we go up. So now we do have some options as to where we could probably put that last electron. We could either pair it up there in the first box, we could go next door and do it. And there is a rule that we follow here, which is sometimes referred to as Hund's rule. And Hund's rule basically says that the most stable arrangement is one where we maximize parallel spins. So earlier we saw that if we put the spins in the same box to go in opposite directions, which is paired spin, which means that would not maximize parallel spins here. So the way that we can maximize parallel spins is actually to put the next electron in the box going in the same direction, which means it's going to be parallel to each other. And that is basically the rule that you follow when you are filling electrons in a subshell that has multiple orbitals. They basically go in one at a time in the upwards direction until you run out of room. And then you come back and start pairing everybody up. So we don't pair up right up front. Single sort of electron in each of the individual orbitals in a subshell heading in the plus half upwards direction. Then we come back. That means that the quantum numbers for this guy will be n is equal to 2. L should equal here what? 1. M sub L is going to equal 0 as it's sitting in that middle one. And our M sub S here will be plus 1/2. Any questions on that there? All right, might as well finish out the first row there, or second row, I guess. So we'll go nitrogen next, which is 7. So we'll go 1s2, 2s2, 2p3 in this case. And here our orbital diagram, again, not drawn based on energy, drawn based on page conserving. Through my page here. All right, so we're going to go up, down, and now to maximize our parallel spins, we will put that last electron over there in that orbital at the end in the upwards direction. That's going to give us a n value of 2. L value here is still going to be 1 in this case. Our M sub L value will now be plus 1. And our M sub S will be plus 1/2 in this case. Again, because it's pointing upwards. Continuing on to the next one, which is 8. So we're going to do oxygen. We'll do 1s2, 2s2, 2p4 in this case. Doing our orbital diagram here. All right, so we'll go up, we'll go down, we'll go up, go down, up, and now we're out of room to maximize our parallel spin. So we do go back to the first one here, and we go in the downward direction here. So our quantum numbers for that one at the end should be n is equal to 2, as it's still the second energy level. Our L will still be 1 because it's in a p subshell. Our M sub L is now back to -1 as it's sitting in the px shell, our orbital. And our M sub S in this case is going to be -1/2. That is what's going to make it different than our guy up here, which had +1/2 basically. Any questions on that one there? All right, so then that brings us to we got there fluorine next, which is 9. 1s2, 2s2, 2p5. So 1 up, down, up, down, up, now down, and down here for our last one in the middle. And giving us our n is equal to 2, our L is equal to 1. Our M sub L is now back to 0 as it's sitting in the py orbital in the middle there. And our M sub S being -1/2. So lastly here we have neon in that second row. And Neon is 10, which would be 1s2, 2s2, 2p6. That is, as you can see, going to fill up our p subshell or 2p subshell there. So up, down, up, down. You can go in up first. Then we're going to come back and pair off. And that is going to give us an n equals 2, an L equals 1. M sub L, we're now back to +1, and our M sub S would be -1/2 in this case. Yeah. Any questions on how to write electron configuration, orbital diagram, assign quantum numbers to specific electrons? So you can see you could get very specific with quantum numbers, as I mentioned. If you're talking about a specific electron, you could also do more general quantum numbers, like, when you're just asked some electron on the energy level, fourth energy level or something like that. And again, if it is asking a question about a specific electron and what their quantum numbers are, they do need to be specific numbers that you choose. They can't be ones like, L could be 0, 1, 2, or 3 or something like that. You got to, based on that electron, pick the correct number. Again, if it's a more general question, like, electron on this particular energy level, then it's possible it could be any orbitals that are on that energy level. So you can't give all the numbers, but it can't be very specific here. Any questions on that there? All right, so why don't you do one? Why don't you write the electron configuration for calcium, which is 20, and why don't you also give the 4 quantum numbers for the for the 16th electron that's there. All right, so you don't have to draw the orbital diagram. You can write the electron configuration, but then also figure out what are the 4 quantum numbers there for the 16th electron that goes in there. Look here and see. So we'll start with just electron configuration. So we should be rolling something like 1s2, 2s2, 2p6. Again, if you count up the top numbers there, that is 10 electrons that you've used. So we got 10 more to go. After 2p6, that's going to be a 3s2. That will then be a 3p6. That is 18 electrons at that point. Now the next one that comes is 4s2. So remember that the S's there come before the D's in that little zigzag diagram that we were looking at. So you want to make sure you get the right one. That should be the electron configuration there for calcium. Any question on that one there? So we're looking for the quantum numbers for the 16th electron. So that is 2 electrons, 4 electrons, 10 electrons, 12 electrons. So to me, the 16th electron should be right in there as that goes through 18. So if you want to just draw the diagram there, or the orbital diagram for our 3p, we have 6, which means coming into there, that is 10, 12. That would be 13, right? That would be 14. That would be 15. And that would be 16. That would be 17. That would be 18. So the 16th electron is actually that one right there. And that means that the n value here should be what? 3? Yes. The L value should be, not everybody at once. The L value here should be 1. Our possible values for L in this case would be 0, 1, and 2 with an n value of 3. 0 represents the s orbital, 1 represents the p orbital, and 2 there would represent the d orbital. So we could see that our electron is sitting in the p orbital, so L can only be 1 in this case. It cannot be all 3 letters. So our numbers has to be only that 1. Yeah, question? What's that? Why isn't this electron? Is that asking? Why isn't the 16th electron? Is that what you're asking?
Yeah.
Yeah. Because of the way they fill, right? So they fill one at a time in the upwards direction, right? And going into our P subshell, we had 2 electrons, right? 4 and 10 and 12, which means when we start filling our P orbitals, that's going to be electron 13, right? It's going to be the first one that goes in, and that would be 13, right? Next would be 14, because that's the way they go in, right? That would be 15, and then our 16th electron would be that one. Yeah, so it's really important to write that Hund's rule, how they actually fill, rather than just counting 2, 4, 6, right? When you go through there, right? So they do go in a specific order, which means the 16th actually ends up being the one at the front. Yeah. 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 Other questions? Okay, so L is going to equal 1, and we can see in this case that it is sitting in that first p orbital, which is the m sub L here would be -1. And we can see that it is pointing in the downward direction, which means it would have a -1/2 for the spin. Also for this spin, it cannot be plus or minus a half, because we're specifically talking about that second electron in there. And the only possible spin that it could have would be -1/2. Yeah. Question on writing electron configuration, doing any of that? Yeah. Now, another thing that comes up with electron configuration is there is sort of a shorthand that's sometimes used. So if we do look at, say, calcium that we got going on here, if we look at calcium up to here, that is, if we count up the electrons up on top, 18 electrons. And if we go to the periodic table, the one that has 18 electrons is argon. So we can't put argon in little brackets there and continue on with the electron configuration, and we can do argon 4s2. This is sometimes referred to as noble gas configuration. And that implies that what needs to go in the bracket should always be a noble gas, which is group number 8, the very last group on the periodic table. Helium, neon, argon, krypton, those guys. That's the only one that should go in there. And then you can continue on with the electron configuration, do sort of a shorthand in that situation, if you like. But it's always the noble gas that comes right before whatever you're writing the electron configuration for. Questions on that there? So again, if we looked at something like sodium, which has 11, it'd be 1s2, 2s2, 2p6, and then 3s1. Again, looking at the configuration up until this point, that is 10 electrons, which means that that is the same as neon's configuration, 3s1 in this particular case. Any questions? Now, if we do end up with something, which question? We did not, because in this case we were looking for the 16th electron, and the 16th electron was in the 3p subshell. Yep. Other questions? Okay, so if we do have something that has a charge, we do have to adjust our electron configuration for those charges. So we talked about cations that have positively charged, and that is made by really losing electrons. We have anions, which have negative charge, which is a result of gaining electrons. So if we look at, say, our sodium there that we just looked at, which is 11, 1s2, 2s2, 2p6, 3s1. Sodium, which is group number 1 on the periodic table, will pretty much form a +1 charge always. And because it has a plus charge, that means it has lost electrons. And because it has a +1 charge, it means it has lost 1 electron from the neutral, which means really sodium here has 10 electrons. And that would give it an electron configuration of 1s2, 2s2, 2p6. Or that is also Neon's configuration, right? And if we look at something, say, like oxygen, that we also looked at earlier, which had 8 electrons, 1s2, 2s2, 2p4 in this case. Oxygen, which is group 6, will always form a -2 charge, which means it is minus, so it has gained electrons. It has 2 more electrons than what it started with, which means instead of 8 electrons, it also has 10 electrons. Which is 1s2, 2s2, 2p6 are also Neon's configuration. All 3 of those things, sodium with a +1 charge, oxygen with a -2 charge, and neon, they all have the exact same electron configuration. Yes, so they all have 1s2, 2s2, 2p6. They're what are referred to as being isoelectronic with each other. Isoelectronic means they got the same electron configuration happening. That is pretty much how metals and nonmetals, when they come together, bond. Yes, that's really the whole purpose of bonding. As we'll talk about in the next chapter, the whole purpose of bonding is for everybody to not become a noble gas, but to basically end up with the same electron configuration as a noble gas. Noble gases are really stable. They're chemically inert, which means they're not interested in reacting because they're frankly really stable. They don't really want to. So the way that everybody else sort of achieves that through bonding is in the case when a metal and a non-metal get together, the metal will lose electrons. And what will happen is it will end up at the same electron configuration as the noble gas that comes before it. And non-metals will gain electrons and end up at the same electron configuration as the noble gas that comes after it. And we're talking about representative elements. Transition metals are a little bit different, but representative metals, things in group 1, group 2, and group 3 on the periodic table, that's pretty much what happens. They go backwards to the noble gas before it and go forward to noble gas after it if it is a non-metal by gaining and losing electrons. Okay, so phosphorus there is 15, I believe. And with a -3 means that it should have gained 3 more electrons. So that's going to make it go from 15 to 18 in this case, which would be 1s2, 2s2, 2p6, 3s2, 3p6, or that is the same configuration as argon in this case. By accepting those 3 electrons, it's able to move itself to that noble gas configuration. It doesn't, again, become argon because in order for it to become argon, it is not electrons that would have to change. What would have to change? Protons, right? So no protons are being changed here. It's just getting itself to the same sort of electron arrangement as that. It is still, again, phosphorus. Aluminum here is 13. And in this case, we have a +3, which means it has lost 3, which will turn that 13 into a 10. And that will give us the same guys we got above there. 1s2, 2s2, 2p6 are Neon's configuration. Any questions on how to write electron configuration for things that have charges? So you just need to adjust your electron configuration. And if it is, again, a representative metal or non-metal, probably should end up at a noble gas in terms of its configuration. Yeah. Okay. Then we kind of comboed a bunch of stuff. So let's take a look and see what we got going on here. All right. So this is what we did earlier, but just to look at again, if we had n is equal to 3, determine the number of allowed subshells for a given one. So for an n is equal to 3, this is a more generic question. So all possible values of L are in play, 0, 1, and 2. which is our S, our P, and our D orbitals that's available in that case. Again, because we're not talking about anybody specific, so they could be in any one of those orbitals on that particular energy level. And obviously, as we talked about last time, for each of those L values, you can do an M sub L value for each individual L value that you have. Now, if L is equal to 2, once again, we were talking about an M sub L that goes from minus L, which in this case would be minus 2, to minus 1 to 0, to plus L, which would be plus 1 and plus 2. L would equal 2, which is a D set of subshell. And that is why we have here our 5 D orbitals basically represented, each one represented by a different number there in this case. Any questions on that one? Again, this is more specific, more generic sort of question rather than specifically talking about an electron. All right, that we looked at last time. That we talked about opposite spins, Paulies exclusion rule. Those we talked about here as we went through that. All the stuff we kind of talked about as we did our electron configuration. So we're gonna pick back up, I think. All right, we're gonna back up about talk a little bit about the periodic table, but before we do, we're gonna talk a little bit more about electron configuration and really the transition metals and sort of what happens with them, and then we'll get to really our periodic table and what's on there. So another principle is the off-ball principle, which is as protons are added one by one to the nucleus, and sort of a build-up principle. That again is how electrons are basically added to orbitals. We build it up from lowest energy to highest, and there's our oxygen that we did there, and our Hund's rule, and our orbital diagram as well here. All right, so let's talk a little bit about a couple of things here. Valence electrons that we could also figure out from electron configuration. So if we look at our electron configuration here, our 1s2, 2s2, 2p6. On the first energy level, there are 2 electrons. On the second energy level here, there are how many electrons? There are 8. Both of those are on the second energy level. There's 2 in the S, and there are 6 in the P subshell. So there are 8 electrons. The electrons in the outermost energy level are what are referred to as valence electrons. They are the highest energy level electrons. They're really important, valence electrons, because they are the ones really involved in bonding. They're the ones on the outside, furthest away from the nucleus, which also means they're not held as tightly, which means they're able to kind of move, be lost, or sort of accepted in that region, are shared. So they are really the ones that are involved in bonding. The other electrons that are closer to the nucleus and held a lot tighter are these guys in the lower energy level. These are what are sometimes referred to as core electrons. And core electrons are those ones that are in those lower energy levels, closer to nucleus, which means, again, they're going to be held a lot tighter from that attractive force to the nucleus, and they're not going to be able to be sort of ripped off, if you will, to be involved in bonding. So it is only really the valence electrons. So you can figure out the number of valence electrons from the electron configuration, which seems like a long thing to do. The much easier way is to look at the periodic table, and as we talked about the other day, we have group numbers, which is group 1, group 2. We skip the middle. 3, 4, 5, 6, 7, and 8 coming through here. And just for reference sake, this is like boron over here and aluminum. Now, everybody in group number 1 has 1 valence electron. Everybody in group number 2 has 2 valence electrons. 3, 4, 5, 6, 7, and 8. So if you want to really quickly figure out how many valence electrons an element has, it will equal its group number. For transition metals, which are in this region, is a little bit different than that, but the group number equals the number of valence electron. So for example, here we have 10, and 10 is neon, which is over here in group number 8, which means it has 8 valence electrons. We did 1s2, 2s2, 2p6, 3s1. That was our sodium, right? Sodium has how many valence electrons? It would be 1, which is this guy on the 3rd energy level, right? And sodium is over here, right? Group number 1, so it has 1 valence electron. So a really quick way to figure out valence electrons is it should equal the group number. Those are definitely important in electrons, as we'll talk about in the next chapter in bonding, as those are the ones that are really involved in bonding. Any questions on that there? All right. Yeah. No, they're typically considered any ones that are not valence electrons. Yeah. So, for example, they're if we went over to say bromine, for example, bromine has 7 valence electrons, and it would all the ones kind of below those would technically be considered core electrons. Yeah. Other questions? Okay. So this is electron configuration and the periodic table, and you can, if you sort of know what you're doing, count off electron configuration off the periodic table, but there are some things that you should be aware of. And we'll look at the periodic table. So if we look at the periodic table, we have our groups. And again, starting over here, really with lithium, although hydrogen is there, but lithium's group number 1 coming down. Group number 2, group number 3, 4, 5, 6, 7, and 8. And we also have our period numbers, right? 1 through 7. If you remember, our N number, our principal quantum number, is 1 through 7, and they match up to the 7 periods that we see on the periodic table. So there is the S block, which is basically these two groups. S has 2 electrons you can put in there, 1 electron, 2 electrons. The P subshell has 6 electrons you can put in it. It starts at group 3 to the end, 1, 2, 3, 4, 5, and 6. The D sort of shell or block is actually the transition metals in between here, between group 2 and group 3. It has 10 electrons in the D, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And down here, these are our F block down here, which has 14. So if you count the number of boxes, there's actually 14 boxes on the bottom. So you literally can sort of count off electron configuration from the periodic table. Again, if you sort of know what you're doing, there are a couple of places you have to be careful of, as you can see on this map here. So for example, if we were going to do our sodium, which is right here in this box there, our sodium here would be 1s2 there to helium, right? 2s2, 2p6, 3s1 in this case, yes. If we were going to do calcium, which is right there in that box that we did before, again, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. This is our D block, and D starts on what energy level? 3. So that's 3D, even though it's on period 4, it is 1 behind the period number. That's 3D, 4D, 5D, 6D coming this way. These 2 rows on the bottom, which are our F block, really do go right here, which is period number 6. But F start on the 4th energy level. So that's really 4F, and below it is 5F. So it gets a little crazy in the middle there. You want to make sure, you could kind of figure it out. My recommendation would be do the zigzag thing that we made earlier and do it that way. You probably will be in good shape. There's a lot of places where you can go kind of wrong if you're not paying attention to sort of what you're doing, but you can sort of count off electron configuration as well. For example, if we did iron, which is right about there, I think. If we did iron, it would be, that's what we'll do. We got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now we remember this is 3D, 1, 2, 3, 4, 5, and 6. Yeah, just count the boxes, and that would get you your configuration. Question? Yeah, so for transition metals, which I think we're going to talk about here in just a second, but for transition metals, it's a little bit different. Most people will consider they have two valence electrons in a sense because it's the s ones that actually are lost first. Some could say they could have upwards of 12, so they really don't follow sort of a good pattern, depending on which one you're sort of talking about, and that'll become more clear in just a second when we get to that slide, I think. Other questions on that? By the way, we're talking about valence electrons. How many valence electrons does helium have? It only has 2. Even though it's part of group 8, it only has 2 total electrons, which means it can't have 8, right? So that's sort of an exception, obviously, for group 8. It will only have 2 valence electrons since that's the grand total it has. Everybody else in group 8 will have 8 valence electrons as well. All right. All right, so we did a bunch of practice, so we're going to skip these here and talk about the transition metals, I think. So let's talk about transition metals, which I think will hopefully answer your question here in a second there. So transition metals have incompletely filled d subshells, or they give rise to cations that have incompletely filled d subshells. So there is several exceptions in the transition metal region that you should be aware of. The two major ones that most of the time people talk about is chromium and copper. And chromium copper, which is 24 and 29, have one extra electron in the d orbital and one less electron in the s orbital, and it's been found to be more stable in that arrangement. And that is because of the very close proximity of those orbitals. So when electrons go in terms of filling, they do fill up the s orbitals first, and then they come and fill up the d orbitals at that point. So they're super close in energy. And in fact, what actually happens when we start to fill the d orbitals between the d orbitals and the s orbitals is once you actually start putting electrons into the d orbitals, there's actually a switch in energy that occurs. And as you fill the d orbitals, the s orbitals actually become higher in energy in that case. And this gives rise to a couple of things that sometimes people do that are incorrect, perhaps, but not really necessarily truly incorrect, but incorrect for this class. And most chemistry classes that you do, you may see somewhere along the way, if you're searching around, you may see electron configuration written like 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2, and kind of all in order, right? Rather than the proper filling order of the 4s2, 3d6, or something like that. And that order is written in terms of energy, which it is correct in terms of energy. After the electrons have gone in, there is that switch that occurs. And sometimes people will write electron configuration where you see basically all the numbers line up like you would imagine all the 3s are together and all the 4s. And you should not write that electron configuration in this chemistry class, or probably any chemistry class you take. There's only one chemistry class I ever took that the guy wanted us to write like that. But it is based on order. We write electron configuration, and most people write electron configuration based on filling order, how they go into the atom, rather than energy. And so there is a slight difference in that. And that's why you may see it somewhere where it is written based on energy, and you'll see the order be slightly different, but we should not do that here. You should do it based on the little zigzag guy we did where the 4s's come before the 3ds and so forth. Now, because of that, to your question, when we talk about sort of valence electrons, what actually happens when we fill sort of those transition metals is when they go to lose electrons, they will always lose those s electrons first. But if they need to then lose more electrons than just those two, which transition metals can do, then they will go into their d electron orbitals to dig out those electrons. So that's why a lot of people will sort of consider them to have 2 valence electrons, but some will say they could have upwards of 12 really, because you put 10 in there and the 2 sort of s's, but nobody really has a plus 12 charge usually. So, you probably wouldn't use them all, but that's why we really don't worry too much about the valence electrons in transition metals. It really doesn't come in play in terms of bonding or anything like that, but that's sort of the rule. So for example, speaking of that, we just did iron right a second ago, which was 26, I think still, right? And we did our electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6 in this case. Now, iron, if it was to make a +2 charge, it would then have 24 electrons. And what's going to happen because of this switch in the energy that happens when we put those d electrons in there, when we fill it up here correctly, so it looks something like this. We are going to actually lose these electrons here. And the correct configuration for iron with a +2 charge would be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. The 4s2 electrons are gone, as those would be the electrons that they lost. Or you could do a little argon 3d6 if you like. So what happens now if, say, iron actually made a +3 charge? So if iron had a +3 charge, it would then have 23 electrons, which means it actually needs to lose 3 electrons from its neutral state. It will again lose the 2 s electrons, which would be these 2 guys right here. At that point, the next place it could get that 3rd electron from is it's got to go into the d orbitals at that point, and it's going to take one of those electrons out, and that would leave you a 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, or argon 3d5. So now you can see what I was saying just a bit earlier. This is a transition metal. It has lost electrons. Did it technically end up in a noble gas configuration? It did not, right? So transition metals don't typically end up at like a noble gas configuration. Only the ones that are representative metals, which again is basically group 1, group 2, and aluminum, basically group 3 on the periodic table. Those guys, when they lose electrons, they end up at noble gases. Transition metals actually do not end up at noble gas configuration when they lose electrons in that situation. Question on that there. All right, so coming back around to a couple of exceptions, and that is chromium and copper. And chromium has 1 extra electron. So normally if you followed our little zigzag guy for chromium, you would get 4s2, 3d4, but again, it's found that an extra electron up there, so you do need to know that guy. And also copper has a very similar sort of exception. It has 1 extra electron in the D, 1 less electron in the S. So if you think about chromium, that's going to really maximize its parallel spin by putting basically 1 parallel electron in each of the d orbitals, and also in the s orbital, we got a parallel sort of electron going on. And for our copper, it will actually kind of pair up everybody in that situation. There actually is a lot more exceptions to electron configuration. If you look on the periodic table below chromium and below copper, if you kind of go down in the middle, things like silver, PD, MO, all those guys, there's a lot more of these sort of exceptions where you see extra electrons up into the D and less electrons in the S. Something like PD over there, I believe, has actually no electrons in the S. They've all been promoted up to the D. So there's a lot of very similar type of exceptions that we see there. So if we look at, here's some of those exceptions. And as you can see here, we see their PD has none of them. They've all been promoted up. So for us, you should be aware, most of those are found, like I said, kind of below chromium and copper. Things like silver as well as an exception. But for us, you'll be responsible for really just these two here for sure. So chromium and copper are the two on the right, and that is how you should write the electron configuration for those two. Again, just knowing that there are more exceptions underneath that, keep that in mind. But for this class, you could just write it following the zigzag thing. You don't have to remember all the sort of exceptions, and there is a lot of them kind of bundled in that little area of the periodic table. Any questions on that there? Uh, no, so the shorthand for iron with no charge, I think is what you're asking. It would be argon. You still need the 4s2 3d6. And so that is the difference, as you can see, between these two, right? The 4s2 were used to make the +2 charge in that case, and that's why they're gone. Yeah. Other questions? All right, so chromium, copper, you need to know the exceptions. And why don't you do nickel with a +4 charge? What the electron configuration would be. Nickel with no charge is 28. Nickel, no charge is 28. Yeah, let's take a look. So we'll start with nickel with no charge here. So nickel with no charge has 28. So that's a little 1s2, 2s2, 2p6. 3s2, 3p6, 4s2 again coming first, and then 3d8. Or you could do again argon 4s2, 3d8. Now, nickel with a +4 charge means that it has lost 4 electrons, which means this guy here has only 24 electrons. Because this is a transition metal, we are going to take 2 electrons from the S because they should be really higher in energy and being lost first. That also means that we do need to actually take a couple of electrons out of there as well. And that would get us basically here our 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 in this case. Or that would be argon. No, 4. Argon 3d6. Any questions on how to write electron configuration for transition metals? Transition metals with charges. Again, you want to remember that kind of switch in energy, and it really comes into play when they lose electrons. So they do a little bit different than others. Yeah, so I think you're asking why do we take the 4s out instead of just taking it from the last one? Yeah. So transition metals are very different than representative metals like say sodium or magnesium, and that's because of when the electrons go in, as we talked about, they do go into the S first, and then they start filling those D. And at the point of filling, the 4s orbital is actually lower in energy than the 3d orbital. But once the 3d orbital starts to sort of fill with electrons, they're actually really close in energy to begin with. What ends up happening is they do actually switch energy levels, basically, or energy positions. And the 4s orbital actually will end up, once the electrons kind of go into the atom and fill the atom, they will actually end up in the higher energy level than the 3D. And that's different than how they go in, but once they start filling and get filled, there's that switch that happens. And really where it comes into play is when something like a transition metal wants to lose electrons. people always lose electrons. Pretty much their highest energy electrons go out first. So because there's that switch in energy that occurs with those orbitals, and only in the transition metal region is where that happens, the highest energy electrons are actually the S's. And that's why we take from the S first. But the S really only has, for example, 2 electrons possible that you could take out in this situation. But in this case, we actually need to lose 4 electrons total. So once we eliminate those 4s, the only next highest place would be the 3d. So that's why we go into the D next and take them out of there. And that only, again, happens with their transition metals because of that kind of switch in energy level that occurs between the S and the D. And by the way, that switch in energy level occurs for all the transition metals. So for example, if you go below on the periodic table there, SC, the next period below it, to the left there where it's strontium and RB, that's 5s, and next to it would be 4d. So when those guys in the 4d transition metal region lose electrons, they will lose their 5s first and then the 4d. And that pattern follows all the way down in the transition metal. They basically will always lose those electrons to the left on the periodic table, the s's first, and then if necessary, if they need more, then they will start taking out the D. And that happens for all the transition metals as you go through it. Yep, other questions? All right, so speaking of the periodic table here, let's officially talk about the periodic table. That's the periodic table, looks lovely. So the periodic table is a couple of things that we talked about. We have groups, or if you're old like me, families. Nobody really calls it families anymore, but they call it groups. And depending on the periodic table, there are different numbering. So as you can see on that one versus, say, this one that's up here, there is different numberings. A lot of times there's sometimes an A numbering and a B numbering that you see. And most of the time we use the A numbering, which is sometimes referred to as the representative numbering. And that is group 1, which is here. Group 2, which is here, group 3, group 4, group 5, group 6, group 7, and group 8. Once again, though, a reminder that group 1 does start with lithium, although hydrogen on pretty much every periodic table is sitting above it. It is not a member of group 1, and we'll talk why that is in just a second. Periods, as we talked about, there are 7 periods which go left to right on the periodic table. We talked about it previously, but the number above the symbol on the periodic table is the atomic number, which is the number of protons, right, that each atom has. And as we talked about it, every element has its own atomic number, its own number of protons, which is, again, if you know the protons are the atomic number, you should know what element you're talking about. Now, the periodic table is broken up into basically 3 parts. There are metals, nonmetals, and metalloids, or sometimes referred to as semi-metals. On most periodic table, I think they drew it in by hand there, you'll see some type of staircase sort of happening over here by boron. And coming to the left of the staircase are metals, which are good conductors of heat and electricity. They could be pulled into wires. They have a shiny appearance. Most metals at room temperature are solids, except for mercury, which is a liquid, which is why mercury, for example, on that periodic table there is blue, and usually a different color on most of them, but most all metals are solids. Upper right here of the staircase is nonmetals. And the staircase itself, which kind of comes down in 2s, and some books, I don't remember if your book includes it or not, but some books will include boron as being part of the semi-metals, are semi-metals or metalloids. And over here is hydrogen, and that's lithium. Hydrogen is what type of metal? What type of element? It is a non-metal. It's really not a metal, right? So it's a non-metal, and everybody else in group 1 is a metal. So that is why hydrogen is not part of group 1, even though it's hanging out there. It's hanging out there because hydrogen has special properties. Years ago on old periodic tables, they would actually throw hydrogen on both sides. You see it on both sides. But nowadays, they kind of keep it just over there. But important to remember, hydrogen is actually a non-metal and not part of group 1, which are other metals. Non-metals, on the other hand, have basically the opposite characteristics. They are bad conductors of heat and electricity. They're dull, they're brittle. A lot of non-metals have a more varied sort of state. Some are gases, some are solids, some are liquids. And a lot of the nonmetals are those diatomic molecules we saw earlier on, like H2, N2, O2, Cl2, F2, Br2, I2, right? So a lot of those guys are nonmetals, and most of those guys are gases. Some are liquids, and some are vapors as well with a liquid component. Now, metalloids, which are also sometimes referred to as semi-metals, are found on that staircase. And really the deal is they have properties that really fall on either side. So the same metalloid can have properties that are very similar to ones that you find in metals. And that same guy could also have some properties that are very similar to what you see in nonmetals, which is really why its position is right about here between the two, basically. So they can have sort of characteristics that fall on their side. Semiconductors, right, are sort of in that sort of area. They got kind of properties that fall both ways. Now, there's some groups do have special names, so you do need to know these. So group 1, which again starts with lithium, these are your alkali metals. Right next door, which is group 2, is your alkaline earth metals. The word alkaline means basic. Yeah, and that is where we get a lot of our strong bases from, like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide. So pretty much if you put OH with anybody there in group 1 and 2, probably going to end up with a strong base. And that's what the word alkaline means. Coming over here to group 7, these are our halogens. And these are the guys we looked at the other day in lab. These are the guys that come as 2s, are fluorine, chlorine, bromine, iodine. And right next door is our noble gases. And noble gases is group 8 on the periodic table. That's our helium, our neon, our argon, our krypton, our xenon, all of our ons. And those guys are pretty much what everybody aspires to in terms of their electron configuration, and really the whole basis of bonding, both types of bonding, ionic bonding, covalent bonding. It's all about getting to the same electron configuration as those noble gases. Our transition metals is another important spot, which is between our group 2 and group 3. And those guys, as we just talked about, are guys that can have a variable type of charge, a lot of them. They also, again, have that D block of where they begin. The 2 rows on the bottom are lanthanized and actinized because, again, that is technically where they should go. I've only seen one periodic table ever that they put them in the right spot and it takes up the whole wall because they have those and then everything else is to the right. But those guys are on the bottom. We don't deal too much with those guys on the bottom. A lot of this is where we find our radioactive guys on the very bottom row there, and a lot of where our man-made sort of elements end up. So we don't really deal too much with those guys on the bottom, but those are the lanthanides and actinides. And as we just saw there, they are basically the F block on the periodic table in terms of electron configuration. So you do need to know, obviously, the periodic table. You do need to know the groups, which way groups go, which way periods go. You need to know where the alkali metals are, the alkaline earth metals, the halogens, and the noble gases. You also need to know where transition metals are, and metals, nonmetals, and metalloids. Any questions on any about there? All right, we will lay it up there for today.